All right, good morning, everyone. So we got a couple more things to talk about before we can do our review for the exam and talk about all that good stuff. So just reminding what we talked about yesterday. So we said that, remember, the change in potential energy is equal to minus the work done, which means if the work is done by the electric field, then that's equal to minus Q times the integral from A to B of the electric field dotted by the differential length. Or if we define this idea, which is called the electric potential, instead of electric potential energy, that's the electric potential energy per unit charge, then this thing says then that the change in electric potential is then equal to minus the integral from A to B of the electric field dotted by the differential length. So okay, all that means is that this is my point A, this is my point B, then we're integrating along some pre-described path where that is a differential line segment dl. So here we have to know what the electric field looks like prior to actually doing this integral. So this one says that we can determine the potential difference between this point and this point if I know what the electric field is and I integrate along the electric field. Okay. However, if we know what the potential difference is everywhere along some sort of space, this says that we can actually then determine the electric field by taking minus the gradient of the potential in 3 dimensions, or if this is only 1-dimensional, so for example, if it only varies in 1 dimension, this is a simple derivative of the potential in that particular direction. So again, this guy's a scalar, this guy turns it into a vector to make it then an electric field. So let's do one example of this, so we can see how this actually works. And then we'll talk about equipotential lines and then potentials for point charges, and then we'll be done. We'll be good enough for tomorrow. Okay. And whatever's left on this chapter we'll have to do for the next exam, so should be fine. So this says, what is the magnitude of the electric field at point 2 in the x direction, -2 in the y direction, and 4 in the z direction, meters, if the electric potential is given by this function? So here we're told that the electric potential, which is then a scalar field, which depends on x, y, and z, is then equal to 2 times the position x times the position y times the position z squared. So this is our potential function. So we want to know what is the electric field, first of all along all space, and then finally, what is it at that particular point? So good, so here we're told that the potential is then equal to, so let's write it this way, the function of x, y, and z is equal to 2xyz squared. So the first thing we need to know is, what is the electric field anywhere throughout the space? So we now know the electric field is equal to minus the gradient of the potential, which means this is equal to minus the partial derivative in respect to x of the potential in the I hat direction, minus the partial with respect to the y of the potential in the j direction, minus the partial derivative of the potential with respect to z in the k hat direction. Now, I mentioned this yesterday, partial derivative basically is just something fancy which says that I'm only seeing how my function varies in one direction while keeping other directions constant. Which means that when I'm taking the partial derivative of the potential with respect to x, y and z are held fixed. They are constant values. Which means when I take the derivative of this guy with respect to x, or at least the partial with respect to x, y and z are simply constants, which means they're constant. So the only thing I take a derivative of is with respect to x, which means this first term then is going to be equal to what? Minus 2yz squared in the I hat direction. Now, when I take the partial with respect to y, x and z are then held constant, which means when I take the derivative of this, I'm going to get simply a 2xz squared. So it's going to give me a minus 2xz squared in the j hat direction. Finally, when I take the derivative with respect to z, at least the partial, again, we hold x and y constant, take a derivative of this with respect to z, so that becomes a 2z. So finally, this becomes minus 4xyz in a k hat direction. Okay. So this is my electric field as a function of position anywhere throughout my space. So this is what my electric field looks like. But we're not just happy with that. What we want to do is know what is the electric field at a given point, which is given by 2, minus 2, 4. Which basically means that anywhere I have an x, I'm going to put in a 2. Anywhere I have a y, I'm going to put in a -2. And anywhere I have a z, I'm going to put in a 4. So let me switch slides and do it over here. So it's going to become 4 times 2, 4 is then equal to, let's go back. So then I have a minus 2yz squared in the I hat direction. So this is minus 2 times y, which is negative 2, times z squared, which is 4 squared in the I hat direction. Then I get a minus 2 x times z squared, so that's going to give me a 2 times z squared, so that's 4 squared in the j hat direction. And then finally I get a minus 4 times x, which is 2, times y, which is minus 2, times z, which is 4, all in the k hat direction. Okay? So the first one, I have a negative times a negative, which then makes it a positive. So that first term is positive. And the second term is negative because I only have one negative. And the third term is also positive because I have 2 negatives, which give me a positive. So ultimately, this is the same thing as what? 4 times 4 squared, which is the same thing as 4 cubed. So this first term is simply a positive 4 cubed in the I hat direction. The second term then is what? Minus 4 cubed in the j hat direction. And the last term then is going to be what? Positive 4 times 4 times 4, which is a 4 cubed. So this is positive 4 cubed in the k hat direction. Anybody know what 4 cubed is? What's that? So this is then 64 times I hat minus j hat plus k volts per meter. Good. So that's it. Not too bad. Nice and easy. So again, this is partial derivatives. Partial derivatives seem scary, but you'll see them in Calc 3, except for Molly, who doesn't need to take Calc 3. Everybody else in this room needs to take Calc 3. So you'll see this in Calc 3, partial derivatives. But again, all it means is that you hold everything else fixed and you see how your function varies in one direction in a multi-directional sense. So here, this is specifically 3 dimensions. It could be 2 dimensions. It could be infinite number of dimensions. It doesn't matter. It just means you hold any other dimension constant while you vary in that direction. What's up, Reed? Sure. No problem. Okay.
What were the units on that?
Volts per meter, because it's an electric field. Yeah, so remember, electric field has either volts per meter or newtons per coulomb. Either one of them are the same. Doesn't matter which one you use. Doesn't matter, they're the same thing. There's no conversion from one to the other one. It's exactly the same. Good. So the next question we have then is, why do we care about potential? So why are we even bringing this thing up? Well, we're bringing this up because, as we've seen in lab, potential is actually intimately related to the electric field. Okay? So ultimately, the reason why we care about potential is because if we know the potential, we know the electric field. But there's more than that. The other thing is because it's easy to measure. All we need is a voltmeter. The voltmeter then tells me exactly what is the value, or at least the potential difference between 2 points at any point. And on top of that, not only is it easy to measure, it's a scalar, which means I don't care about direction, which means it has no directional property to it at all. It's something easy to measure, it's a scalar quantity, and it's intimately related to the electric field. So how is it related to the electric field? Well, it's related by, as you guys know from lab, equipotential lines. Let's talk about equipotential lines. So what's an equipotential line? So an equipotential line or equipotential surface, as we talked about in lab, is a line or surface. So I'm going to write a surface slash line where every point has the same potential. Which means if I had an equipotential line that looks like this, what this means is that every point along this line has identically the same potential. So let's say this is potential, I don't know, V1. Right. So what does that mean? So what that means is if I had a particle, let's say here's my particle charge Q, and I move it along this equipotential surface from this point here, so let's call this point, I don't know, x1, to some final point over here, let's call that point x2. This means if I start off here on the equipotential surface and I move it from this point to this point, that means my change in potential must be equal to 0. Well, we now know that our change of potential is equal to the change of potential energy divided by the charge, which is also equal to minus the work done divided by the charge, which means if the potential, change of potential going from this point to this point is equal to 0, so is the work. So that means if I move a particle along an equipotential line, I do no work. Neither does the electric field. I can do it for free. Life is great. That's the same idea as if I had my water bottle here, do it in front of the camera so these guys can see. If I have my water bottle here to move it from this point to this point, how much work was done? Nothing. At least by the gravitational field. Because here, the gravitational potential is the same as the gravitational potential here, which means the gravitational potential energy is 0, at least the change of it, because it's moved along a constant surface. This would be an equipotential line as far as the gravitational field is concerned. So what does that mean? Well, what that means is, so if my change of potential is equal to 0, that means the minus integral from A to B of the electric field dotted by the differential length must also be equal to 0. But that's the same thing as minus the integral from A to B of the magnitude of the electric field times the magnitude of dl times cosine of the angle between the two. So what does this tell me? So this tells me that what? If I move my particle from one point along an equipotential to another, this expression of the integral has to be equal to 0. Well, let's talk about this. So for this thing to be 0, either the electric field has to be 0, dl has to be equal to 0, or cosine of theta has to be equal to 0. Okay with this? But first off, can the electric field be equal to 0? No, if I have an equipotential line, I have to have an electric field. So in general, I have an electric field which is pointing somewhere in this figure. Is dl equal to 0? Well, no, I moved it from here to here. So dl can't be 0. So that means the only thing here that could be equal to 0 in general is this term, the cosine of the angle. So what does this tell me? Well, this tells me that if cosine of the angle is equal to 0, what angles of cosine give me 0? So for what angles is cosine equal to 0? 90, 270, or plus or minus pi over 2. So what does this mean? So what this means then is that what? If I have an equipotential line, any point along there has the same potential. That tells me then that what? The electric field then must be perpendicular to that equipotential surface. That's what this thing ultimately tells me, okay? So from here, this thing implies to me then that the electric field then must be perpendicular to the equipotential surfaces. Not only that, this negative sign here also tells me the direction of the electric field then points from high potential to low potential. So this is the utility of knowing the potential. Again, number one, it's a scalar, it's easy to measure. Well, it's a scalar. Number two, it's easy to measure because all I need is a voltmeter. Number three, I know the electric field is perpendicular to the equipotential lines at every point. And number four, the direction of the electric field points is from high potential down to low potential. So what does that mean? So that means that if I knew exactly what the equipotential surfaces look like, for example, let's say I have something that looks like this. I can then uniquely determine the electric field. So how would I do that? Well, what I know is at every point along anywhere of these, the electric field must be perpendicular to that. So here I have a perpendicular, 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 perpendicular. draw a few, perpendicular, perpendicular, perpendicular. So what that tells me then is that my electric field lines have to do something like this. What does that tell me about the charges that are creating this surface? There are two charges of equal charge, or at least of equal sign of charge. Here what's happening is that the electric field lines are curving away from each other. So what I have to have are two charges which are both either positive or both negative. How do I know if they're both positive or both negative? Well, if I am also told that this is, say 10 volts, this is 9 volts, this is say 8 volts, 7 volts, etc., then I know the electric field has to point from high potential down to low potential. So in this case, these would have to be negative charges. So the equipotential surfaces tell me exactly what the electric field looks like. Okay? Tells me exactly what is the charge which is creating this electric field without ever having to measure the electric field directly. So the utility basically of potentials is the fact that, again, it's a scalar quantity, it's easy to measure, it is perpendicular to the electric field, and it points from high potential down to low potential. So knowing everything about the potential will tell me everything about the electric field. So I'm going to give you a visual demonstration of this. I'll put this onto Blackboard so you guys can play with it. So this is an electric field simulator. But this will simulate many different things. So for example, I can simulate the equipotential surfaces. Each one of these lines then is an equipotential surface. From here, we can then generate the electric field lines. The electric field lines then point perpendicular to the equipotential at any particular location. If you want, I can also put the vector directions in here and make it all look pretty. So this is one particular configuration. I could get rid of all these, choose a different one. So let's look at a quadrupole. So again, equipotential surfaces. Electric field lines have to be perpendicular at all different points. Throw some vectors on top of there so you can see the directions. So by knowing the equipotential surfaces, we know everything about the electric field. So this is why we actually care about potentials. Okay? So one more thing we want to talk about, and then we'll be done so we can actually do a review. We just have to look at potentials of point charges. So let's look at potentials of point charges. Like I said, I'll put that guy up onto Blackboard so you guys can play with that later. You can see all that, how it works. So good. So last thing we want to talk about is the potential of a point charge. So yesterday, we did an example where we had a sphere, which had a charge Q, which had a radius of R, and what we said was that at some radius R away from it, relative to spatial infinity, so we have R is equal to infinity out here, we found that the potential was equal to KQ divided by R. So this is what we actually found. Now, due to the spherical symmetry of a point charge, there's actually no difference between a point charge and a spherical object, right? If I had a spherical shell or a sphere, then the potential outside of that is exactly the same as a point charge. So the reason we actually did this as well is that this is also the potential of a point charge. Now again, this potential here is actually delta V is equal to KQ over R, where this is equal to the potential at a radius R minus the potential at infinity, but the potential at infinity is equal to 0. Okay? So when I simply quote that the potential at a radial distance R away from a point charge is KQ over R, what I really mean is that it's the potential difference between where it's 0, which is all the way out at spatial infinity, relative to this point. So that means that this KQ over R is the potential difference between this point and that point all the way out at infinity. Okay? That's what this thing actually means. So it turns out that potentials at a given point also satisfy the superposition principle. So this means if I had a bunch of point charges, so let's say this is Q1, Q2, Q3, Q4, and I want to know what is the potential at some point P here. Well, the total potential then is simply equal to the superposition, or the sum, over all the individual potentials at that given point. So the total potential at that point P is simply then equal to the total potential at that point. So each one of these guys has a distance of R1, say, R2, R3, and say R4. Now, again, the nice thing about potential, though, is that since potential is a scalar quantity, not a vectorial quantity, I don't care about direction. All I care about is the distance at which it is away from that point and the sign of the charge. So notice here when I write out potential, I'm not putting absolute values around that potential, which means if the charge is negative, the potential is negative. If the charge is positive, the potential is positive. But since this guy's a scalar quantity, I never have to care about direction. There is no directional properties to this guy at all. Right? Which means I don't have to worry about this guy pointing off in this direction, this guy pointing off this way, this guy pointing off this way, and do a vector sum over all that. None of that matters, because it's a scalar. So let's do an example. So this example says that, this is 7. Okay. What is the potential at point P in the figure below? So here I have two charges. I have one charge of minus 50 microcoulombs at a distance of, 26 centimeters away from the origin. And the second one is the same distance, 26 centimeters away from the origin. Has a charge of positive 50 microcoulombs. And I want to know what is the potential here at point A, a distance 30 centimeters above Q2. So that other one is a distance of 60 centimeters. So good. So let's redraw this. So I have, here's my x-axis. Here's my y-axis. So I have Q1 here, which is equal to minus 50 microcoulombs. I have Q2 here, which was equal to positive 50 microcoulombs. This was what, 26 centimeters? This was 26 centimeters. Point A is right here. This was 30 centimeters. So that this distance across here was 60 centimeters. Good. So again, all I want to know is what is the potential at point A? Well, again, we said that the potential at a point A is simply equal to the superposition of all possible potentials at that point. So here, this is simply equal to the potential from charge 1 plus the potential from charge 2. Now we now know that this is equal to K times the charge Q1 divided by the distance R1 plus K times Q2 divided by the distance R2. So R1 in our case is simply equal to the 60 centimeters. That's the distance from this point to this point. R2 then is equal to 30 centimeters. Okay. So if I plug these values in, the potential then at point A then is equal to K times the magnitude of Q times then, let's do it this way, 1 over R2 minus 1 over R1, where I'm writing Q then as basically the absolute value of Q1, which is equal to the absolute value of Q2, since those two are the same. So let's plug in the numbers. So this becomes 9 times 10 to the 9th times 50 times 10 to the minus 6 times 1 over 0.6 minus 1 over 0.3. Or did I have those guys backwards? R1, no, R1 was negative. Oh no, sorry, R1 was 60. Sorry, 0.3, 0.6. Knew something was backwards. There we go. Good. Plugging my numbers, what I find in this case then is the potential at A works out to be 7.5 times 10 to the 5th volts. So good. So again, here, since this is a scalar quantity, means I don't care about any directional properties to it. There is no sines, no cosines, no anything like that. The only thing that matters is, again, this distance from this charge to this point, this distance from this charge to that point, and the signs of the charges. That's it. There is no scalar, no vector properties to these guys at all. Now let's ask a interesting follow-up question to this. And then this will be the last thing that we're going to do. The interesting follow-up question then is, how much work was required to bring Q2 to its final position near Q1 in this problem? So basically what this means is, let's say initially I have empty space. Nothing's going on. Then what I'm going to do is I'm going to come all the way out here to spatial infinity, grab Q1, drop Q1 now here, go all the way out to spatial infinity on this side, grab Q2, drop Q2 in here, and I want to know how much work did I have to do. How much total work was there required to bring that guy finally into this charge configuration. This is what we want to know. So what was the total amount of work done to set this thing up? Well, so again, here we have, here's Q1, here's Q2, and then I have what, 26, so that's 52 centimeters between the two, right? So the total amount of work it took then to bring in Q2 after I brought in Q1 then is equal to the sum of the work to first bring in Q1, and then plus that of the work to bring in Q2. So that's the total amount of work that we would have to do. So the total amount of work then is equal to the work done to bring in Q1 plus then the work to bring in Q2. Where we know work is equal to minus the charge times the change in potential. Okay. So let's go back to what we said. So initially we have empty space, so nothing exists here. We're going to go out and grab Q1 and bring Q1 in from infinity and drop it at this point. Right? So again, we're going to come all the way out here, grab Q1. What's the potential out at infinity? 0. That's what we defined it to be. Right? So Q1 is going from 0 potential because it's at infinity. I'm going to grab Q1, and I'm now going to drop it in here. But how much potential is now here if I have empty space? 0, right? So what this means is I bring Q1 from 0 potential by definition into a region where it now has 0 potential, which means I have 0 minus 0, which is 0, right? My change of potential as far as Q1 was concerned was equal to 0, which means the work done is equal to minus Q1 times 0, which is equal to 0. I, or the electric field, did absolutely no work to bring in Q1. Correct. What about Q2? Well, Q2, I'm going to come all the way out here to spatial infinity. I'm going to grab Q2, but again, what is the potential out at spatial infinity? 0, by definition, right? So Q2 is initially at 0 potential. Now I'm going to bring this guy in and drop it here at Q2's location. But what's the potential as far as Q2 is concerned? What is supplying the potential at the location for Q2? What is the only other thing in the problem? Q1. So as far as Q2 is concerned, there is a potential here, but that potential is being supplied by Q1. So that means as far as work 2 is concerned, that's then equal to minus charge Q2 times then the final potential, but that final potential is that of Q1 minus the initial potential, which is 0 because it was at spatial infinity. Which means that work 2 then is equal to minus Q2 times simply the potential from V1. So that means the total amount of work it would take to bring in Q2 is then equal to 0 plus the work it took to bring in Q2. So this is then equal to 0 minus Q2 times V1, which is then equal to minus Q2 times K times Q1 divided by the distance between the two, which is 0.52 meters. Now here again, this is 50 microcoulombs. This is 9 times 10 to the 9th, but this one is minus 50 microcoulombs, which means the negative sign from here cancels the negative sign from here, which makes it a positive. So at the end of the day, this thing becomes equal to 43.3 joules. So this is the total amount of work which was done. Now, quick question. If the work is positive here, who did the work? So remember, all this work here is the work done by the electric field. So if the work in this case is positive, did the electric field do the work or did I do the work? So who did the work? Did the electric field do the work or did I do the work? So we talked about this before. See if you guys remember what we talked about. What does positive mean? Does that mean the electric field did it? Or did it not do it? Somebody else had to do it, so I did it. Ask it a different way. Who gets paid? The electric field or me? You? No. I didn't get paid. The electric field did it itself, right? Remember, positive means that in this case, the electric field did it itself. And why does that make sense? What's the sign of the charge on Q1? Negative. What's the sign of the charge on Q2? Positive. What does a negative charge and a positive charge want to do to each other? They want to attract each other. So in this case, since this guy is negatively charged, this guy is positively charged, they want to be close to each other, so the electric field actually brought them next to each other. I was just pretending, which means I don't get any money. I don't get paid. But I would have to do the work if that was positive and that was positive, or that was negative and that's negative. In that case, they don't want to be near each other, so I have to do the work. In that case, this would become negative, because this would be positive, this would be positive, which would make this a negative work. Okay? That's it of the new stuff. So let's do a review for the exam. So first things first, we did chapters 22 and 23 together. I made no distinction between those two. So let's talk about those. So here, we first looked at force, right? So we said we had Coulomb's law for the electric force, which was equal to K times the magnitude of Q1 times the magnitude of Q2 divided by R squared. This is the magnitude of the force. This is only true for point charges. If it is not a point charge, I cannot use this. In general, this is equal to the charge times the electric field. This is general. This works for anything. Whether it be point charges or anything else, this guy works for anything. The first one only works for point charges. We also saw that the force on the ith particle was equal to the sum over J of the force on I by J, where J just can't equal I. This is our superposition principle. Superposition. That was about it on that. Good. So the next one we looked at was electric fields. So we said that the electric field, by definition, is equal to the force per unit charge, which means that for a point charge, the electric field is equal to K times Q divided by R squared in the R hat direction. So this is for a point charge. If I have a continuous object, this is then equal to K times the integral of dq divided by R squared in some R hatish type of direction. So this is for continuous, where dq is equal to either lambda dl, eta dA, or rho dV, depending on the symmetry. The last thing we saw in this chapter was we defined a dipole. So this guy has a charge of negative q, this one has a charge of positive q. D is the distance vector which points from the negative charge to the positive charge. The dipole moment then is equal to the charge of the positive charge times that distance vector, which means that P then points this way. This is P. That's my dipole moment. From here, we stuck this guy into an external electric field, and here we saw that this has a torque on it, which is given as the dipole moment crossed by the electric field, and has potential energy, which is equal to minus the dipole moment dotted by the electric field. Now, here, other things you might want to write down, which I don't remember all of them off the top of my head, are things like the electric field of A sheet of charge, the electric field of the ring, and the electric field of the disk. Write all those down just to be on the safe side. So for example, as I was talking to one of you yesterday, if I said the problem was I had a charged ring and I put a charge above that and I want to know what is the acceleration that that guy feels, if you didn't write down the electric field from the charged ring, that means you have to use this expression to find it. So now you have an extra 5 minutes to do an integral to figure that out where you didn't have to if you actually wrote it down. So that's it. That's all we did in these two chapters. Right? Now, this is a chapter to be careful of because if you just kind of go through the book and you write down any random crap that the book says is an equation, doesn't mean it's an equation. Because a lot of times the book likes to say that, an equation would be this. But again, this is only true in a particular situation. So if you go through the book and you write down any more than these things, just be careful that you know exactly the context of that, what it was used for, if it had constant charge, if it was uniformly distributed charge, etc. Okay? So just be careful of those things. Well, this is it. This is basically all we did in these two chapters. Not too bad, right? Not too bad. The next chapter we looked at was chapter 24, which was Gauss's law. So Gauss's law simply says that the electric flux, which is equal to the integral of the electric field dotted by the differential area, integrated over the surface area of a three-dimensional surface, is equal to the charge enclosed divided by epsilon naught. Now, remember here, there are three types of symmetries that we care about. There is the spherical symmetry, there is the cylindrical symmetry, and then finally there is planar. So, not saying I'm worried about your geometry skills, but I'm going to go ahead and write down the geometries for these guys, okay? So, for the sphere, the surface area of the sphere is equal to 4 pi r squared, and the volume of the sphere is equal to 4/3 pi r cubed. Okay? For the cylinder, it's a little more complicated. So we either have the area for the cap, which is that of a circle, which is pi r squared, or we have the area of the shaft, which is equal to 2 pi r times the length. And in both cases, the volume is equal to the area of a circle, which is pi r squared times the length. Now here, as long as you choose the correct symmetry, what will happen here is that this thing is simply going to become the electric field times the surface area is equal to Q enclosed over the over epsilon naught, which means that ultimately this thing is going to break down to that the electric field is equal to Q enclosed divided by the surface area times epsilon naught. This is where your starting position should basically be. Now, again, the hardest thing about here is remembering these guys, but now we're going to write them down so we don't have to remember them. So that's going to be great. And then just Q enclosed. So Q enclosed will either be 0, because it's either an empty cavity or it's a conductor. Okay. So if you're inside a conductor, remember the charge is equal to 0. Or it's going to be uniformly distributed, which means that the charge is just simply equal to the charge density times the volume enclosed. Or it's going to be non-uniformly distributed. But it's not going to be that one. So it's either going to be uniformly distributed or 0. Okay? So basically, as far as we're concerned, Q enclosed then will be equal to either 0 or the charge density times the volume enclosed. So this is going to be Q enclosed, one of those two. Now, again, with Gauss's law, be careful. If you're dealing with cylindrical symmetry, it has to be infinite in length. If it is not infinite in length, you cannot use this version, but you have to use this version instead. Okay? So if I told you you have a finite length cylinder, automatically you know you cannot use Gauss's law. The only way to use Gauss's law is if that thing was infinite in extent. So that means that you would have to use this integral version instead. So good. And then the last thing is, finally, chapter 25. Here we're going to focus mostly on potential of point charges. So the potential of a point charge is equal to KQ over R. So this is the point charge. This guy, again, satisfies, at a point P, the superposition principle. So P of I. And finally, work is equal to minus the change of potential energy, which is equal to minus Q times the change of potential. And one other thing that could show up on here is conservation of energy, which says that the change in kinetic energy plus Q times the change in potential is equal to 0. So this is conservation of energy. And then all this stuff here is for point charges. So that's about it with potential. Now, since we haven't spent much time with potential and we're just kind of cramming it in now, basically, don't expect too much from potential. So at most, it would be a small part of a long problem. So maybe like a part C, something like that, especially if I'm looking at a bunch of point charges. For example, I might ask you the electric field at a point, the potential at a point, what's the force that another particle would feel at that point, how much work did it take to put this thing together, things like that. So that's pretty much about it for that. Otherwise, it would be something that's a short answer, a quick calculation, but if you're not comfortable with it, just go ahead and skip it. You have other options. So, not too bad. So as I said, so this, even though this stuff will be on there, it'll be on there very minimally. So again, this is either going to be a very small part of a long problem, or a short answer, quick calculation problem. So basically things like that. So what that basically means then is that the entire exam is going to focus primarily on electricity, right? So electric field stuff. So that means that first thing we can tell right away, and I already told you this before, this will definitely be a long problem. So Gaussians Law will definitely be a long problem. So look for things like what's the electric field on the inside of the object, what's the electric field on the outside of the object, with a uniform charge distribution. Again, if it says that it's a conductor, automatically you know the electric field is equal to 0. Okay, so remember that part. So that's definitely going to be a long problem. Another long problem will be continuous charge distributions. Now, again, for this guy, I'm not testing your integration skills. All the integrals will be on the first page that you need. So basically your job then is to set up the integral, switch to the first page, find the integral that best represents what you wrote down, copy that solution then onto the page, evaluate it at the bounds, and then life will be great. That's about it. Okay? So finally, the last long problem will involve electric fields from point charges. What else? Forces from point charges. Superposition. And I'll circle this one in here too. So basically a whole bunch of stuff about point charges. So electric fields from point charges, potentials from point charges, forces from point charges, all that kind of good stuff. So that's the third long problem. So what does that mean about dipoles and stuff like that? So dipoles here is going to be a short answer quick calculation problem. So that'll be true. As I said, some of the stuff here will show up as short answers. I forget what some of the other ones are, so I'll have to do some modifications. But yeah, so that's pretty much about it. So again, one long problem will definitely be Gaussians Law. One long problem will be integrating over a continuous charge distribution. Another long problem will just be fun with point charges. And so you have a bunch of point charges, different configurations. So now find the electric fields, things like that. So one thing when it comes to electric fields and forces with point charges, again, don't forget about symmetry. Anytime you don't have to calculate something because they should automatically cancel them. So again, if you have 2 electrons, for example, equidistant away from a particular point, the electric field at that point has to be 0. Because the electric fields are in opposite directions. Equidistances, they're going to cancel out. So anytime you can use symmetry to your advantage, use it. Okay? So don't calculate things that you don't have to calculate. Okay? That brings up then the extra credits. So one thing I'll tell about the extra credits is that, again, it'll be fun with forces between point charges, but there will be harmonic oscillation mixed into it. I love harmonic oscillation. Sorry, Rich. It's one of my favorite things. Sorry, Mom. She gave me a dirty look too. Okay. Everybody's okay? So any questions about the exam or any of that kind of good stuff? So again, any constants, things like that. So the charge of an electron, the charge of a proton, the mass of a proton, the all that kind of good stuff, K, et cetera, et cetera. Don't worry about any of those things. I will give you all of them. And the last thing is, I set up 2 more group assignments for you. So how many are we up to now? I know I give you 3 Gaussians Law ones. I give you 1 continuous electric field one. There was an electric field with force into it, and then there was at least 1 other one, right? Plus these 2, so we're at least somewhere between 8 and 10. I don't remember exactly how many, so I'll count them, but I'll get all that set up tonight so you can submit all of those tonight. But these are the last 2 I'll put up. So the first one says that we have 2 electrons which are fixed 2 centimeters apart from each other. Another electron is shot in from spatial infinity and stops midway between the 2. So it wants to know what is the initial speed of that third electron which is shot in from infinity to stop there between the 2 charges. This is conservation of energy. So all you're using is conservation of energy, using the fact that the initial, or the electron which is at infinity goes from 0 potential to a point now has potential from 2 other electrons. That's basically it. Okay? The second one then says, in the diagram below, point P is at the center of this rectangle here with the potential equal to 0 at spatial infinity. So it wants to know what is the net electric potential at point P due to these 6 charges. Now, one thing, this is a negative sign here, so this is actually negative Q3. Now, when it comes to potential, be a little bit more careful than you were with electric fields, because with electric field, what we said was that this guy and this guy would actually cancel each other, because from here, this electric field will point this way, this electric field will point this way, so these 2 would cancel. But with potentials, that's not true anymore. Because with potentials, it depends on the sign and only the distance, which means that these 2 are equidistant. They're also the same sign, which means the potentials don't cancel each other at this point. They simply sum together. So the total potential from these 2 at this point is twice the amount of potential from one of them. But since this one is Q3, this one is negative Q3, then the potential from this guy and this guy do cancel each other here because the charges are opposite in sign. So it's different than with the electric field, because with the electric field, this one had an electric field pointing this way, this one also had an electric field pointing that way, so they would sum together. So be a little bit careful. So again, it doesn't depend on direction, it only depends on the signs of the charges. Same thing here. So these 2 would actually sum together instead of cancel each other out like they would with an electric field. So just be careful of those things. But again, there's no directional property to it, so we don't have to worry about those. Well, that's about it. So 2 kind of nice, easy problems. Give you a little more extra credit points going into the exam. As I said, we have somewhere between 8 and 10 points at this stage. I don't remember exactly how many. This is up on Blackboard too, so you can find it there. Right there this morning. Okay. So, any questions? You guys doing okay? Feeling scared of this thing? Now, the good thing is after we get out of this, we'll do a little bit more with continuous charge distributions for potentials, but then after that, we go pretty much to nice, easy things like circuits. So after this, we'll pretty much go to mind-numbing algebra without little thought to it. Okay, so basically mindless algebra. So next exam usually goes up nice and high. So, but again, this one shouldn't be too bad. It's not too difficult. Concepts are kind of easy, but again, it's scary because it's going from things which are definite particles moving to now talking about fields. So you're still trying to wrap your head around fields while I'm hammering you with an exam. But again, when you come back to this at the end of the semester, you'll look at it and be like, why did I think this was so difficult? So next exam, like I said, will be nice and easy. Mindless algebra. After we go through that, we're going to go into magnetic fields. So we're going back to all this stuff here. Like we'll be good. But by then, it'll be old hat. It'll be nice and easy. All right. So I'll see everybody then tomorrow. So I'll get a Blackboard set up so you can do all of the group assignment submissions, do the extra credit submission, all that good stuff. Life will be great. Stop this.